Hello, welcome to today's video where we are going to present the essential standards and remediate the information that you need to know from the AcidsBases reaction rate and equilibrium unit. Before we get started, you're going to need to grab some materials on which you can take notes from this video. And then before you come to the Pride session, you will also need to print the homework assignment that is posted right below this video. Do that homework assignment and then check your answers and be ready to ask questions as you get together with your teachers and clarify this content in order to be ready for the replacement test. Today what we're going to do is we are going to cover 4 essential ideas and concepts and mathematical processes, the things that are most important in the last unit. Those include the ability to identify what acids and bases are, and then identify their conjugates in the Bronsted-Lowry sense of acids and bases. Then you'll be looking at rates of reactions and how reaction rates can be sped up or slowed down. And this ties into what we call the collision theory of reaction rates. And then finally, we'll be talking about chemical equilibrium. We'll talk about Le Chatelier's principle and how Le Chatelier's principle can be used to determine how reactions at equilibrium respond to stress. And then we will also be talking about how to represent chemical equilibrium mathematically by writing what are called KC expressions. So to get started, as we pick these off one at a time, we're first going to talk about acids and bases. You may remember from class that there are actually 2 definitions of acids and bases that we use, the Arrhenius and the Bronsted-Lowry definitions. The only one that you need to know for remediation is the Bronsted-Lowry definition of an acid. In the Bronsted-Lowry way of understanding acids, we understand that acids are hydrogen ion donors. Now, you may also remember that we talked about the idea that hydrogen ions are the same as protons. So to help you better understand this, consider a hydrogen atom. Hydrogen is element number 1, meaning it has 1 proton, and it has a mass of 1, telling us that it has no neutrons. But for this to be a neutral atom, it would also then need 1 electron orbiting that nucleus, as we've drawn here in blue. Now, when we talk about hydrogen as it relates to acids and bases, we're not talking about hydrogen atoms, we're talking about hydrogen ions. And when we take this hydrogen atom and make it an ion with a positive charge, the way that we do that is by removing an electron. And so when we pull that electron off of this hydrogen atom to make it a hydrogen ion, now the electron's gone and the only thing that's left is a proton. So as we talk about hydrogen ions, what we're really talking about is individual protons. And in the Bronsted-Lowry sense, acids donate these protons. Then bases are proton acceptors. So bases will take in hydrogens from the acids. So as you might imagine, the general form of this reaction then is an acid, which is a hydrogen loser, will lose a hydrogen ion to a base, and the base will accept that hydrogen ion. What happens from that is the base now has an extra hydrogen that it didn't have before, and because it's got an extra hydrogen, it actually looks like an acid. And we call that the conjugate acid, and then the acid, having lost the hydrogen, is now missing a hydrogen, meaning it could take that hydrogen back in, making it a conjugate base. And this was the first concept that you needed to be able to think through and apply relative to remediation. You need to be able to look at a chemical reaction and identify which is the acid, which is the base, and then which are the conjugates. So let me give you these thoughts, and then we'll talk about this practically. So when you need to find the conjugate acid, what you're going to do is you need to remember that conjugate just means new, newly formed. So when we talk about a conjugate acid, we're talking about the newly formed acid, and that simply forms by adding a proton to the base. And then the conjugate base, conversely, is formed when the acid loses a hydrogen. So remove a hydrogen from the acid and what's left is the conjugate base. Now, if this seems confusing, let's look at some examples. And what you'll find is that all you're doing is tracking down hydrogens. So let's look at these examples. So looking at example number 1, the very top one, you'll notice that on the left we have CH3. And then if we look for something on the right side of the reaction that looks like CH3, you'll notice that we've got CH4. But the difference between CH3 and CH4 is that CH3 gained a hydrogen. That makes this the base. Now, when we look at C6H5O6 and find something similar on the right, you'll notice that on the right we've got C6H5O. The difference being that C6H5OH lost a hydrogen. That makes this an acid because acids are hydrogen losers. They donate hydrogens. Now we need to figure out the conjugates. And the way to do this is to go to the acid and remove the hydrogen. And when we do, what's left is what we call the conjugate base. Then to figure out the conjugate acid, what we'll do is we will go to the base and we will add a hydrogen. And when we do, the thing that is formed is the conjugate acid. So the easiest way for me to figure out the conjugates is go to the acid, remove a hydrogen. This is what we wrote in blue. When we remove that hydrogen, the remainder is the conjugate base, and then the other is the conjugate acid. So continuing with this idea, let's clean up this mess, and let's try another one. So now we'll take a look at our first substance, CH3COOH. And when we look for something similar on the right, you'll notice that we have CH3COO. The difference being CH3COOH lost a hydrogen. As we said, that makes this the acid. Now, that of course makes NH2 the base. If one's the acid, the other has to be the base, but we can compare and see that that's the case. If we find something on the right similar to NH2, we find NH3. The difference is that NH2 gained a hydrogen to become NH3. That makes this our base. Okay, so now that we know the acid and the base, it is now time for us to figure out the conjugates. And as I mentioned, the easiest thing for me to do to find the conjugates is go to the acid, remove a hydrogen. What's left is the conjugate base, and that makes the other the conjugate acid. So let's take a look at one more example. If we go down here to our final example, you'll notice that we have HBr. And if we take the HBr and find something similar, you'll notice that we've got Br minus. The difference being HBr lost a hydrogen. Again, this makes it the acid. And if that's the acid, that means that water is our base. Once you know the acid, the other one has to be the base. Now, let's see if we can find our conjugates. So to figure out what our conjugates are, again, the easiest thing to do is go to the acid, remove the hydrogen. What's left, in this case Br, is the conjugate other, which is the conjugate base, and then the remainder, or the other partner, is the conjugate acid. So again, that's one of the 4 things that you've got to be able to do as a result of this unit, is to be able to identify acids and bases and their conjugates. Now moving along to the second concept, we are going to talk about rates of reactions and the things that affect reaction rates. Now, don't try to connect this to what we're doing with acids and bases. Right now, this is going to be a standalone concept. So clearing our slate, let's talk about reaction rates. So when we talk about reaction rates, what we're talking about is how fast does a reaction go? How quickly do reactants turn into products? Now, in order to figure out how fast reactions go, we need to first of all answer the question, what has to take place in order for a reaction to occur at all? And the answer to that question is the reactants have got to bump into each other. So say, for example, we're looking at a reaction where hydrogen atoms, molecules, are bonding with oxygen molecules. Well, even a better example, sodium atoms are running into chlorine atoms and forming table salt. Well, what has to happen in order for sodium and chlorine to turn into table salt? And fundamentally, the idea is these guys have got to run into each other. If they don't run into each other, they can't bond, and if they can't bond, they can't form products. So this is what we call the collision theory of reaction rates. And it simply says that for a reaction to occur, the reactants have got to collide. Now, the thing that we've got to understand, though, is that not all collisions lead to reactions. Sometimes these atoms can bump into each other, and it's as if nothing happened. You can think about it as if you're thinking about collisions with vehicles. You understand that if you're in a car and if you're backing out of a parking place and you tap the car behind you, you could tap that car very gently and it would be as if nothing happened. You hit, you bounce off gently, nothing changes, nothing dents, nothing happens. But you also understand that if either of those cars is moving faster, when they collide, there's going to be so much energy in that collision that it's going to cause significant change. Well, the same thing is true when we talk about reactants colliding to create products. If they don't hit hard enough, there won't be enough energy present to cause the reaction to turn into products. So the thought then is this, that when these reactants collide, they have to collide with enough energy to break down the bonds in the reactants, which then allows them to create products. Now the problem is, because there's a minimum amount of energy that they have to have in order to form products, not all of these collisions are effective. If these atoms, if these reactants don't hit hard enough to create products, then it's as if they didn't hit at all. No reaction takes place and no products are formed. So the thing then that determines the rate of the reaction is the number of effective collisions. So the more that these reactants hit hard enough to cause a reaction to happen, the faster the reaction will go. So again, it's not enough for them to just run into each other. They have to hit with some minimum amount of energy, which you may remember we call activation energy. They have to hit with some minimum amount of energy that allows them to break apart and then stick together as products. And if they don't hit that hard, then it's as if they didn't hit at all. No products are formed and the reaction goes slower. So the question then becomes this: what can we do to make more collisions effective? What can we do to a reaction to make it go faster? And the answer is we can actually do one of two things. We can increase the magnitude of the collisions. Magnitude means amount of energy. So we can make them hit harder. The other thing that we could do is we can increase the frequency of the collisions. Frequency means how often they hit. So if we can get the reactants to hit harder, or if we can get the reactants to hit more often, that will make the reaction go faster. So how do we do that? How do we get the reactants to hit harder, higher magnitude, or more often, higher frequency? Well, we actually have three different things that we can do. One of the things that we can do to make them collide, make the rate go up, because there's more effective collisions, one of the things that we can do is increase the temperature. As the temperature of a reaction goes up, the rate goes up. So the question is why? Does it make the atoms, the reactants, does it make them hit more frequently? Or does it make them hit harder? higher magnitude. Well, let's take a look. What is the difference between something that's hot and something that's cold? Well, we know that inside a cold substance, the particles are moving very, very slowly. So they don't hit each other very hard, and they don't hit each other very often. Well, inside of a hot substance, the particles are moving faster. And because they're moving faster, they hit more often, which is a question of frequency, and they hit harder, which is a question of magnitude. So when we heat up a reaction, the reaction goes faster. The reason is because the particles are hitting with higher frequency more often and higher magnitude, more energy. And because both of those go up, more collisions are effective and it forms reactants more quickly. The second thing that we can do to increase the rate of a reaction is we can change the concentration. The relationship is this: as concentration goes up, the rate goes up. So when we talk about concentration, we're talking about how much reactant is present in the reaction. So why would higher concentrations of reactants make the reaction go faster? Is it a question of frequency or is it a question of magnitude? Well, to give you something that you can visualize, imagine a jam-packed football stadium and you being a member of that crowd. And compare that with a plaza in a downtown area, maybe at lunchtime. And so the question that we need to ask is, how will the collisions that occur between the people in the stands compare with the collisions that will occur between the people walking around in the plaza? Well, certainly because the people are more concentrated in the stands. In any given amount of space, there's more people. We certainly understand that the people that are in the football stadium are going to run into other people much more often. You're bouncing against all the people that are around you. Well, if you're out in the plaza, you aren't going to run into people as often because you're more spread out, and as a result, you don't run into people as much. So this would be a question of frequency. You will run into things more frequently, so the higher the concentration of reactants, the more frequent the collisions, and therefore the faster the rate. Notice in this example, magnitude doesn't change. You don't necessarily run into people harder in the stadium as you do in the plaza. So it's not a question of how hard they hit, it's a question of how often they hit. And then the third thing that we can do in order to make a reaction go faster is increase the surface area. And the idea is this, that as surface area goes up, the reaction rate goes up. Again, the question is why? Is it a question of frequency, or is it a question of the magnitude with which the particles collide? Well, imagine this. Imagine if you wanted to start a campfire. And if you wanted to start a campfire, I think we all understand that the way to get a fire going is not by touching a match, a lit match, to a log. We understand that in order for wood to burn, it is a reaction with oxygen. And so to get this fire burning, we need the oxygen in the air to collide with the wood fibers in such a way that a reaction can occur. The problem is that when we think about a log, there really isn't that much surface area. There's the top and the bottom and the sides, but there's not that much surface area. So what we do is we take a hatchet and we take that log and we split it into kindling. And as we break up that log, it exposes surfaces that were not exposed originally, greatly increasing the surface area. If we touch a match now to a piece of kindling, we know that that will burn. So the question is why? Why is it that kindling will burn whereas wood won't? And the idea is that when we chop up a log, we're creating all this additional surface area. And this additional surface area allows the oxygen in the wood to collide more frequently because there's lots of extra surface, there's lots more places for them to hit, and the frequency of the collisions between the wood and the oxygen goes up. Notice that it doesn't mean that they hit harder, it simply means that they hit more frequently. So going back to the idea, we understand that frequency goes up, but the magnitude doesn't, because we're just simply exposing surfaces where they can hit more often. So those are the three ways that we can change the rate of a reaction by changing the frequency and magnitude of collisions. We can change the temperature of the reaction, which makes the particles hit more frequently and with greater energy, magnitude. We can also change the concentration. When we do, that increases the frequency of the collisions without changing the energy or magnitude. Or we can change the surface area. That also increases the frequency of the collisions, but not the magnitude of the collisions. They don't hit harder. Well, it turns out there's one other way that we can change the speed of a reaction, and that's by adding a catalyst. Now, catalysts are interesting. A catalyst is a substance that speeds the rate of a reaction, but when it speeds the rate of a reaction, it is not actually a reactant or a product. It's a substance that is not consumed in the reaction, but it does make the reaction go faster. The thing that's interesting about them is they do not change the frequency or the magnitude of the collisions. So if they don't change the frequency of the or magnitude of the collisions, how do they make the reaction go faster? Well, what they do is they create a new pathway, a new way for the reactants to turn into products, and this pathway has a lower hump, a lower activation energy. So let me show you what we're talking about here. So if we look at this reaction, we have over here the reactants, and over on the right we have the products, and you'll notice that on the y-axis is energy. So what this means is that in order for the reactants to turn into products, they have to collide, and the height of this hump represents the amount of energy that that collision has got to have in order for reactants to turn into products. So if we have a collision between the reactants, and if it doesn't have enough energy to get over the hump, it just comes right back down as if the collision had never taken place. So in order for a collision to take place, the collision has got to get over the hump, then it goes and turns into products. And again, the more collisions that get over the hump, the faster the reaction goes. And again, we understand that we can get more collisions over the hump by getting them to hit harder, magnitude, or more often, frequency. And the way that we can do that is by increasing the temperature, increasing the concentration, or increasing the surface area. Now, there's one other thing that we can do to make this reaction go faster, and that's what a catalyst does. What a catalyst does is makes the reaction go faster, not by changing the frequency or magnitude of the collisions. What a catalyst does is it drops the hump. It creates a different way for this reaction to take place, and that different reaction pathway has a lower hump. And because the hump is lower, collisions that wouldn't have got over the first hump do make it over the second hump, and they will more quickly then go to products. So now, of course, the question is, how do catalysts work? How do catalysts drop the hump? And frankly, that's not something that we talk about in general chemistry. We do talk about it a little bit in AP, but it's not a topic of conversation for general chemistry. Okay, so that is the second of the essential standards that we needed to talk about. We've now talked about acids and bases and conjugates, and we've also talked about reaction rates and how it relates to collision theory. What we need to do then to wrap up this conversation with remediation is to talk about chemical equilibrium. Now, you may remember that we talked about what are called reversible reactions. And in a reversible reaction, we've got reactants, we'll call them reactant 1 and reactant 2, and they turn into products. We'll call them product 1 and product 2. And if the reactants just turn into products and then things stop, this is what is called a quantitative reaction. You run out of the limiting reactant, and when you do, the reaction's over. Now, you may remember from class that in this past unit, we introduced you to another type of chemical reaction. This is not a reaction where reactants simply become products. What happens is all the while that the reactants are turning into products, these products then react together and go in the other direction, and they turn back into reactants. We call these reversible reactions. It's a process where reactants are becoming products, but then the products are becoming reactants, and both of these things are happening at the same time. As that happens, eventually what will happen is the rate that the reaction is going forward and the rate that the reaction is going backwards will become equal. So the forward and reverse reaction rates become equal. So they're moving forward and backward at the same speed. And when that happens, they have reached a condition that we call chemical equilibrium. And when we say equilibrium, that's based on the word equal, but the thing that is equal at equilibrium are the rates. And so we talked about this system that reaches this condition called equilibrium. The thing that you have to be able to do with these equilibrium systems is predict how they respond to stress. So when they're at equilibrium, these equilibrium systems are very stubborn. They want to stay at equilibrium. And so if you come along and do something to an equilibrium system to move it out of equilibrium, it's going to fight you to come back to equilibrium. And this is what Le Chatelier's principle allows us to predict. It says that equilibrium reactions will offset whatever change we make in order to get back to equilibrium. Now, the thing that you've got to be able to do is predict what that's going to look like. And in order to do this, you're going to want to remember the simple little statement, same side does the opposite, opposite side does the same. So what does this mean? Well, let's take, for example, this chemical equilibrium. We have NH3 and HF, and that is in equilibrium with NH4 plus, fluoride minus, and heat. And when we talk about same side does the opposite and opposite side does the same, we're talking about the same and the opposite side of the equilibrium arrow, which is sort of like the center point of a seesaw. And so what we do then is we talk about disrupting equilibria. So for example, say that we've got this reaction and it's at equilibrium, and we come along and we add some HF. So if we add HF, what's going to happen is the amount of HF is going to go up. And you can see this isn't balanced anymore. This thing is now out of balance. So what needs to happen in order for this to come back to balance? Well, in order to come back to balance, what has to happen is the NH3 has got to go down. It's too high. And then the NH4, the HF, and the heat have got to go up. And if we can do that, it will come back to equilibrium. And notice, this is what same side does the opposite, opposite side does the same means. So our initial change, which I just circled there, it's the red arrow, is to increase HF. When we do that, the stuff that is on the same side of the equilibrium arrows, the stuff that's on the same side, the NH3, will do the opposite. If HF goes up, NH3 goes down. Then everything on the opposite side of the reaction, it does the same thing. So HF went up, so does everything else on the other side of the reaction. So coming back to equilibrium, if we increase HF, NH3 goes down, and everything on the other side, NH4 plus, fluoride minus, and heat, they all go up to come back to equal. So let's try that again, and let's try a different example. But before we do, let's then talk about how we talk about this idea of coming back to equilibrium. And what we say is this: when it comes back to equilibrium, everything over here goes up. And because the stuff on the right is going up, we say that the equilibrium shifts to the right. So the equilibrium shifts towards the side that's going up, because that's what it will make more of. Okay, so let's look at another example. Now we're back to equilibrium, and now what we're going to do is we are going to increase heat. At this point, why don't you hit pause on the video, and why don't you draw in arrows to represent what you think is going to happen to NH3, HF, NH4 plus, and fluoride minus. Remember the rule: same side does the opposite side does the same. So hit pause, draw in your arrows, and hit play when you're ready. So welcome back. Let's take a look. So using our seesaw analogy, we know that if heat goes up, this thing will no longer be balanced. So what it wants to do is it wants to come back to equilibrium. So if the right-hand side of this went up by adding heat, to come back to balanced, the things on the right-hand side have got to come down. Notice same side does the opposite. So the stuff on the same side did the opposite of the initial change. Then notice on the opposite side over here, these things did the same as the initial change. So that means that the NH3 and the HF will go up. Then how do we talk about this in terms of an overall shift? Well, you'll notice that it's the things on the left that are going up. So we would say that this then is a reaction that shifts to the left. Okay, so now we've talked about chemical equilibrium conceptually, and we've looked at describing how Le Chatelier's principle allows us to figure out how reactions respond to change. Now we need to talk about equilibrium mathematically. What happens in a system at equilibrium is when these reactants react together, when they reach equilibrium with their products, because the forward and reverse rates become equal, that means that the reaction is going forward and backward at the same speed. Because that's true, the amount of reactant will become constant and the amount of product will become constant or not changing, because reactants becoming product as fast as products turning back into reactant. So what we do is we talk about that ratio. We set up a ratio of product to reactant, and that ratio has a name. That ratio is what is called a Kc expression. So for a reaction at equilibrium, we can measure the amount of product, we can measure the amount of reactant, and by setting those up as a fraction, we create a ratio that's called a Kc expression. Now notice when we say amounts, we're talking about concentrations or molarities. So when we understand that the products are on the right and we understand that the reactants are on the left, by setting up that ratio, we call that a Kc expression. Now, let's talk about how to write Kc expressions. So given this reaction where 4HF reacts with H3BO3, and that's in equilibrium with 3 waters and then an HBF, we're going to write the Kc expression for this. And notice how we write the numerator. The numerator of the Kc expression, which you know to be the stuff on the right, because that's right divided by left, notice what happens. The 3 in front of the water becomes an exponent, and then the plus sign becomes a multiplication sign, which is understood to be there. So we understand that coefficients become exponents, and we multiply and not add. So with that being the case, hit pause and write down the denominator, the bottom of this fraction. So write what the bottom of this fraction will look like, given that we're looking at the 4HF and the H3BO3. Hit pause, fill in the denominator. Okay, now that you had the opportunity to fill in that denominator, let's take a look at what it looks like. And so as you might have predicted, this 4 becomes an exponent, and then the addition becomes multiplication. And so we've got HF raised to the 4th power, and then H3BO3. And notice they're in brackets indicating molarity. So what we can do then, now that we understand this structure, is we can write Kc expressions for reactions and then plug in numbers and solve for things that we don't know. So for example, here we've got a balanced equilibrium system where 2 sulfur dioxides reacts with oxygen to form 2 sulfur trioxides. So if you would, why don't you pause the video and then write the Kc expression for this process. Now that you've had the opportunity to write that Kc expression, remember that these are going to be right over left. And so you'll notice that the top, which is the right side of the reaction, we've got the SO3 squared. Make sure that you see that that squared factor comes from here. And then in the denominator, we've got SO2. Again, that would be squared. And then we've got the O2. And notice that these are all written in brackets and that this is multiplication and not addition because that's the way Kc expressions are written. So now what will happen is they can give us data to fill in these brackets. So this says if the final concentrations in this reaction are SO2 is 0.125, O2 is 0.11, and SO3 is 0.20 molar, what is Kc? So to solve this, we need to carefully plug in these values. Please pause the video, plug in the values, and then hit play. And actually, if you'd like to, why don't you plug in the values and then solve, and we'll talk about the rest of this problem in just a second. So now that you've had a chance to plug in the values, you'll notice that the concentration of SO3 is 0.20 molar. Notice that I did label it molar and that it is squared. Don't forget the exponent. Then the concentration of SO2 is 0.125 molar. Again, that too is squared. Very common mistake was to not put the exponents here or to forget them, moving them down to here. And then the concentration of O2 is 0.11 molar. Doing the math, we take 0.20 squared divided by 0.125 squared divided by 0.11. If you're working on a TI calculator, be really careful with orders of operations, and you'll know that you got it right when you arrive at a Kc value of 23. You'll notice that there are not units for Kc values. They are what we call dimensionless numbers. But don't think that dimensionless means meaningless. This number 23 actually tells us quite a bit. What it tells us is that at equilibrium, there's more of this on top than there is this on the bottom. We know that because the fraction is bigger than 1. In this case, it's 23 over 1. So because the numerator of the fraction came from the right side, the products, what that tells us then is that this reaction favors products. So if you have a Kc value greater than 1, this means that these reactions favor products because products are on top. Now, if you have a Kc value that is smaller than 1, this means that the denominator, the bottom of the fraction, is greater, and that would give you, that means that the reaction would favor reactants. Now notice that this doesn't mean that the Kc value is negative. Kc values cannot be negative because you can't have negative molarities. Okay, so let's solve one more. Similar to the one that we just solved, we're given an equation, and the first thing that we're going to do is write a Kc expression for that reaction. Please write out, well, hit pause and write out the Kc expression for this reaction. Now that you had a chance to write the Kc expression, you'll notice that in the numerator, we have the products, H2 and I2, and in the denominator, we've got the reactant, HI, and notice that it's squared. Now we're given some data, and this time they give us the Kc value, 0.39. And they give us the final concentrations for the hydrogen and iodine, and the question is, what is the concentration of HI? So now they're having us solve for a molarity given Kc and other molarities. So let's plug in what we know. Take a second, if you would, plug in all the data that you're given, and then we'll get back together and solve this together. Hit pause and plug in the data. Now that you've had a chance to plug in the data, you'll notice that Kc is given to us as 0.39. Notice that this Kc value is smaller than 1. So that would tell us that this reaction favors reactants. Remember from our previous slide, Kc values less than 1 favor reactants because reactants are in the bottom of the fraction. But moving along, they gave us the molarities of the H2 at 0.2 molar, 0.20 molar, and the I2 at 0.18 molar. Now what we're solving for is the concentration of HI, and we'll call that X. So in order to solve this, we will cross multiply. We get 0.39x squared, and then we'll multiply 0.20 times 0.18, which is 0.036. Continuing to get x by itself, we'll divide by 0.39. Dividing both sides by 0.39, we arrive at this. And then taking the square root, we end up at 0.30. And notice that this time this number has units on it. It's molarity because we are not solving for Kc, we're solving for a molarity. So there you have it. We've now covered all the information that you need to know as essential information from this unit. We talked about acids and bases and conjugates. We talked also a little bit about the definition of acids and bases, but you only need to know that in order to identify them in equations. After that, we talked about reaction rates and the collision theory, which gives us a sense of how fast reactions happen. Then following that, we talked about reversible reactions and systems that are at equilibrium and how to predict how equilibrium systems respond to stress. That's Le Chatelier's principle, which tells us same side does the opposite and opposite side does the same. And then we learned how to describe equilibrium systems mathematically by writing these product divided by reactant ratios, which are called Kc expressions. What you'll want to do now is, if you haven't yet, print the homework assignment that is posted on our website. Do that homework assignment and then check your answers, which are posted online. From there, you will then need to come to one of the 2 remediation sessions that are listed on your invitation letter. In order to get in, you will need to bring with you the notes from this video, the homework assignment that you printed and completed, and then also your remediation invitation letter. You'll then come to one of the 2 remediation pride sessions. Remember that your letter is your excuse note to come to get into pride to come to that. During that time, you'll receive further instruction. We'll answer questions. Then you'll have another homework assignment. Completing that homework assignment and checking your answers online will then be the prerequisite for getting into the replacement test. The time and date for the replacement test is also given on your letter. So we will then see you for that replacement test later on this week. So if you have questions, be sure to address those with your teachers. Thank you for taking the time to engage in this material, and we look forward to seeing you later this week.